Given, 4 arrays, land start time, land duration, water start time, water duration. Describe every land and water ride. You must experience exactly 1 land ride and 1 water ride, in either order. Each ride opens at its start time, but you may wait. When a ride begins at time t, it ends at t plus its duration. After the first ride, you start the second as soon as it is available. Goal: the earliest time both chosen rides are finished. Example 1. Land ride 0 opens at 2 and lasts 4, so it finishes at 6. Water ride 0 opens at 6, so we board immediately and finish at 9. That land then water plan beats every other pairing, so the answer is 9. Example 2. Water first finishes at 11, then land ride 0 starts right away and finishes at 14. Land first would finish at 8 but forces water to wait until 18. Water then land is best, output 14. To minimize our total completion time, we have exactly 2 structural choices. We either ride a land ride first and then a water ride, or we do the exact opposite. Because these 2 sequences are completely independent, we can think of them as 2 separate problems. Let's look at what happens when we choose to go from a land ride to a water ride first. If we pick a specific land ride, it finishes at its start time plus its duration. But when can the next water ride actually finish? It depends entirely on whether that water ride is already open when we arrive. If it is open, we start immediately at finish land. If it is not open yet, we must wait until its official opening time. In both cases, the final finish time is the max of when the first ride ends and when the second ride opens, plus the second ride's duration. If we have thousands of rides, testing every single land ride against every single water ride means checking n times n combinations. With constraints up to 5 times 10 to the 4th, a brute force pairing will easily crash past our time limit. We need a way to decouple these choices. Can we optimize one side without knowing the details of the other? If the land ride finishes after the water ride opens, the final time is directly driven by FL. If the land ride finishes before the water ride opens, the final time is entirely bounded by the water ride's own timeline, SW plus DW. In neither case does a larger FL ever help us. To minimize the overall finish time, make FL as small as possible. This means we don't need to match every land ride with every water ride. For the land and water path, scan the land array once to find the single ride that finishes the earliest. Once we lock in that best finish time, pass it forward and check it against each water ride to see which yields the best final result. What applies to land first applies exactly to water first. Find the earliest finishing water ride independently, and check how it pairs with every land ride. Take the minimum result of these 2 independent pathways for the global optimum. You are now ready to build the algorithm. To build our solution, we first set up a dashboard to track our records. We initialize our best total time to infinity because we want to discover the minimum possible time. We also set up 2 slots to track the absolute earliest completion times for a single standalone land ride and a single standalone water ride. First, we scan our land rides. We visualize each one on a timeline by adding its start time and duration to see when it ends. Land 0 finishes at 6, while land 1 finishes at 9. We want the quickest exit, so we lock in 6 as our absolute best land finish time. We do the exact same thing for the water rides. We scan our options, and here we just have one. Water 0 starts at 6 and takes 3 units of time, finishing at 9. This is our earliest standalone water finish, so we lock it into our dashboard. Now we simulate our first full journey, land then water. We take our best land finish time of 6 and pair it with our water ride. Since the water ride opens exactly at 6, we can jump right on without waiting. It takes 3 units of time to complete, finishing at 9. This becomes our current best total time. Next, we check the reverse journey, water then land. We take our best water finish time of 9 and pair it with both land rides. Because both land rides open before time 9, we are forced to start them at 9. Land 0 finishes at 13, and land 1 finishes at 10. Neither of these beats our existing record of 9, so our best total time stays 9. With both pathways fully checked, our dashboard holds the definitive winner. Our minimum finish time is 9. By treating the two paths independently, we avoided checking every single combination and solved this problem in linear time. N is the number of land rides and M is the number of water rides. Time is O of N plus M, 1 pass over land, 1 over water, then each pairing direction in linear time. Space is O of 1, using only a few scalar trackers. First we initialize the answer and 2 best finish trackers to infinity. Then we scan every land ride and every water ride, keeping the earliest finish time for land alone and for water alone. Next we simulate land then water. For each water ride we start after the best land finish, add its duration, and tighten the answer. We run the symmetric water then land pass, then return the minimum finish time.